Hi, everybody. My name is Jordano Mark. I am a senior developer at Dremio, located out in Seattle, and I'm here today to discuss with you guys a new feature called Apache Iceberg clustering, which extends upon the foundation that the Iceberg spec already has and builds upon partitioning, but it benefits on some of the weaknesses that partitioning has and carries with it. Considering the packed agenda, I'm not going to be able to go through all the things that clustering provides in terms of benefits, but my goal here is to provide you guys a high-level summary of some examples of how clustering outperforms partitioning, then introduce some illustrations on how clustering actually works. Oh, it's not transitioning. There we go, okay. So my goal here is to provide some illustration as an examples of clustering, and hopefully by the end we can have some trade-offs identified on how clustering can outperform partitioning, but then also identify weaknesses that come along with it. So let's get to it. Let's imagine we have a table called Sales 2024 that exemplifies the sales of an electronics store. We choose to partition this table by month. So what we have is a set of folders, January through December, where all the data will be organized based off of this structure, right? If we were to run a query that says, hey, give me the data or the rows from the first 2 weeks of December, what partitioning will do is, because we organize this in the sake of months, we don't even have to scan through anything in January through November, one of the benefits that partitioning has, right? One of the problems with this is it's built on the assumption that the data that you have is uniform or evenly distributed across all the months. In an exaggerated example, just for simplicity, if we were to zoom into those folders and see the data files that are extended inside of them, of the partition folders, we may recognize that all these files, maybe averaging about 300 megabytes, are scattered across the table, but specifically the December folder, its partition has a lot of data, maybe over half the data in the table. If we were to run this query where we benefit from partitioning, January through December, or January through November, sure, we get to remove a certain set of data files, but there's still an abundance of data that we have to scan through. This is what we consider a data skew, and our customers are faced with this often. One of the solutions we provide to this is clustering. What exactly is clustering? It's a data layout strategy that organizes rows based off the values of one or more columns which you decide, similar to partitioning, without physically splitting the data into these rigid folders, right? Everything that this feature is built on is founded by what's already existing in the Iceberg specification. Specifically, we're going to take advantage of the manifest entries min-max column value ranges, and which are provided by the Parquet files footers. The goal is to prevent overlap between these min-max value ranges. So if we were to rewind and imagine this Sales 2024 data as a cluster, if we were to rewind this table as, instead of being partitioned, instead clustered by date, you won't have these rigid structures of January through December folders. Instead, all the files will be loosely scattered across the table. And we may be able to recognize that, okay, January through June kind of exists in this space. July through November exists in this arbitrary space. And the bulk of the data in December exists in the table as well. But if we were to run the same predicate select query statement that asks for the first 2 weeks of December, not only do we get to prune out January through November, but we also get to prune out the second half of December as well. Let me go a little deeper into how this is working. So here's a figure. On the left side is the table December specific data files from the partition table and the dates min-max ranges of that file. File A may show that the min-max range of the partition table is between December 1st and December 23rd. File B, December 7th through the 30th, and so on. With the partition table and the query predicate that we've assigned of December 1st through 14th, we can skip out file D entirely because it doesn't match the range of the predicates assigned. So we don't even have to scan it. We can just look at the footer and acknowledge, okay, hey, nothing in here is valuable. Let's move forward. Okay, on the clustering side, what we have is the data instead is the min-max ranges range from the 1st to the 16th, the 16th to the 19th, the 20th to the 23rd. This is different from the partition table because you may recognize that through file A and file C, there's overlap in the min-max value ranges, which requires us to have to scan file A through C. Meanwhile, on the clustering side, we only have to scan one file. We get to skip the others. Okay, so how exactly does this technology work? The goal is to identify hotspots, and with that, we need to define a terminology called clustering depth. Clustering depth is the average number of data files that overlap within a file's min-max value cluster index. So when I say something has low clustering depth, that indicates that the data is well organized. There's not a lot of overlap between those min-max value ranges. If something has a high clustering depth, that may indicate that the data is scattered across various data files, which means that we can't effectively prune out files. We have to instead scan them. It affects read performance. So let's go through this example. We have, let's say these files in this little micro example are the ranges of files and their dates. So file 1 has a range of the 1st of the month through the 4th of the month. File 2 is the 5th through the 8th, and so on. If we were to define a clustering depth for file 1, we would consider this depth to be 1, because it does not overlap with anything. File 2 has a clustering depth of 2 because it overlaps with file 3. File 3 is a bit tricky because, yes, it overlaps with 2 between the date 7th and the 8th, but we want to look at the place where the most depth worst case scenario occurs, and that's how we define the clustering depth for that, which happens on the 11th of the month in this case, because it overlaps with file 4 and file 5. So we have a clustering depth of 3. And similarly, file 4 and file 5 also have a clustering depth of 3 because of the overlap on the 11th of the month. This gives us an average clustering depth of the total amount of depth per file divided by the total files existing within this micro table. Optimized engines with clustering will aim to minimize the depth to as close to 1 as possible. Dremio and many other engines have a data maintenance schedule. For us, that's known as like the optimize command. And, we have something called an optimize command. And the goal of the optimize command is to perform this reorganization across the data files and their paths, or in their min-max ranges. But it's important to note that when you do this optimize command, you don't want to reorganize the entire table. Because if the table is very large, you have to deal with, you're going to strain the engine, right? And you may not be focusing on the things that are important depending on your table schedule and what you are trying to do with it. So instead, what we do is an incremental process where we're going to treat it like triage and focus on the locations in the table that have the highest amount of overlap and focus on that first. And then maybe next time, whenever that may be, that you choose to optimize your table again, it'll then focus on whatever's the next highest priority. So let's go through an example of that. Going back to our visual that we have before, there are many things that can happen during this optimize command with clustering, depending on the file sizes and the ranges of overlap. But let's imagine in this case that we have files that are very large. So we can't do an optimize command all in one go. We have to do an incremental process. If we were to do this, an example that I could provide is something that would be an iterative approach of maybe 2 optimize commands happening over the sequence of time. Phase 1 represents the first optimize call. Phase 2 represents the second, right? In phase 1, it may recognize, hey, okay, these files are way too big to do in one call. We're going to split this up into highly prioritizing what's most important. And in this case, we have file 2 and file 3. We're going to specify that as the subgroup. And then we're going to specify file 4 and file 5 as a second subgroup. And we're going to handle those 2 independently in the same iteration. So when we actually perform the cluster, the overlap that once existed between file 2 and file 3 is no longer present. And the one that existed between file 4 and file 5 is now assessed as well. This is an example of maybe one iteration of optimize. But there is still that overlap that existed between file 3 and file 4 back in the beginning of the table. That's now identified as cluster group 1, file 2, and cluster group 2, file 1. There's still overlap there. So this is an example where on the second iteration, whenever you call optimize again, it is able to grab those set of files and create a new cluster for that specific overlap. And as a result, through 2 iterations of optimizing your table, you have a table that's clustered and well organized based off of the min-max ranges of your specified cluster keys. One question that's common is, well, how many iterations do you have to perform to get your clustering depth to an optimal state? This is an example running through our engine where the data is somewhere between a gigabyte to hundreds of gigabytes. And of course, this can be different as your data scales. But you can see that after the first to second, maybe the third iteration, the clustering depth of these tables dramatically drop. This is great, but it's important to also note that there are setbacks of this. When you're doing optimize calls, you're causing a lot of data rewriting, which can be high computing and can also degrade performance when you run these optimize commands. But the investment in the long term results in a table that's well organized throughout whatever your cluster key is defined. So that gets us to kind of the overall summary of what we've been able to exemplify today. The main one that I want to emphasize that we showcased in this presentation is the enhanced pruning on the reads, right? But with that, there is the degradation of performance that happens when you run an optimize command, as well as the high compute that comes along with it. Now, there's a lot of examples that I cannot showcase today for the sake of time, but there are many that are equally as important, if not more important, depending on what our customers' needs are with their tables. And with that, I highly encourage you guys to take a look at this QR code, and it maps to a tech blog that basically goes over all of this that I provided in the presentation, but in much more depth, giving you guys detail about what's behind the hood, lower level, what's really going on between these constructs of space filling curves, as well as best practices for how you can get started on your engines to be using this feature, as well as cautionary tips. And with that too, as we mentioned, you guys, oh, isn't on there. Okay, well, Alex Merced had a QR code. You guys have them close to your guys' shares. All of this is, if you scan that QR code, you'll also get access to the definitive guides of not only Apache Iceberg, but Apache Polaris. It was the first thing that I read when I wanted to get into the Iceberg space, and I think it's a great read. I highly encourage you guys to check it out. So with that being said, I have about 1 minute for questions. If anyone has questions, feel free to shoot away. So, any questions?
Okay,
right here.
Like roughly how long does the clustering take to run?
So the question is, how long did the clustering take to run? It's going to be dependent on the size of the table. I couldn't give you a specific set. It's also going to be dependent on how much compute you have within your engine, right? So I can't give you a definitive answer for that. It's going to be highly dependent on the configuration of your table, as well as the user configurations that you specify. Any other questions? Yes?
What is the candidate for the column with this partition cluster keys?
Yeah, so the question was, what is the candidate for a cluster key? That is something that is going to be dependent on the state of the table. For the example that I provided over here, back in the very beginning, it's going to be dependent on what you're intending to query for, right? If you are going to be doing a lot of predicate pruning based off of the column, based off of a specific column, that might be an indicator that that's a great clustering key to use, right? Because you get to take advantage of this capability of pruning your data so you no longer have to scan the data between January through November, right? So usually if you're finding predicates in the where clause with a specific column, that might be a good indicator of when to use that as a clustering key.
But that's just for one, like not available.
Yeah. So this is what you're getting into is what happens if you want to define multiple columns as clustering keys. This is something that I did not get to talk about in detail, but there is this mathematical construct called space filling curves in Z ordering. I'd recommend taking a look at that blog. I don't have any more time today. Thank you guys for the questions.
Round of applause. Thank you very much. Thank you.